In the last video, we got introduced to quantum mechanics with some of its quirks. I mentioned the uncertainty principle, and because it's so important, it deserves a special video. The topic of this video is therefore the general uncertainty principle, and we will discuss a key aspect of why quantum mechanics is fundamentally different from classical physics. In order to properly understand the general uncertainty principle, it is necessary to first introduce the viewer to operators, which are essential in quantum mechanics, though before we can do that, we first need to take a step back to classical physics. In classical physics, we have a continuous number line of values to choose from. We can describe the position, momentum, mass, etc. with numbers from this number line. Thus, at the end of the day, position, momentum, etc. are all just numbers. Most of you have probably not thought about the possibility to consider something different, but the truth is that numbers are rather simple mathematical objects in the sense that they commute. To commute means that it doesn't matter what order you multiply the numbers. If you multiply 4 times 2 or 2 times 4, the result in both cases is 8. Not all mathematical objects have this property, like for example matrices, but let's not get into that. The fact that classical physics is based on numbers means that in classical physics things commute. In quantum physics we replace the numbers with operators. These we can understand like processes. Let's consider a rather brutal analogy to why processes are fundamentally different than numbers. Assume you want to go bungee jumping. To do this, you must do two things. Put on the safety equipment with the bungee cord attached and then jump. Notice the enormous difference between first putting on the safety equipment and then jumping, compared to the other variant of jumping and then putting on the safety equipment. The difference is literally life and death. In quantum mechanics, the situation is similar. The order of considering the operator or process is very important. In quantum mechanics, it's therefore important to consider what operators commute and which do not. If operators do not commute, then it is of interest to figure out their commutation relation, or the difference in considering operator A and then B compared to considering B and then A. This we can express as in brackets A, B is equal to AB minus BA, where the head signifies that A and B are operators. In a quantum mechanics course, you might be asked the question, what does it mean for an equation to be quantum mechanical? And the answer would be to see if the equation is defined in terms of operators. That is why you promote your usual objects like position and momentum to the position and momentum operator in quantum mechanics. It turns out that doing this promotion corresponds to setting the x hat equal to x and the p hat is equal to minus I h bar times the derivative with respect to x, where x hat is the position operator and p hat is the momentum operator. Now we can try to compute the commutation relation for this case, and doing so we find that x commuted with p is equal to minus x I h bar, the derivative with respect to x, plus I h bar, the derivative with respect to x, times x is equal to I h bar. So we can see that it does make a difference if you first consider the position operator and then the momentum operator, compared to doing it the other way around. This is a fundamental difference in quantum mechanics, and we will see this result later. Now that I've introduced operators, we are ready to tackle the general uncertainty principle. There are many operators one can come up with, but a certain amount of them belong to a special case of operators called observables, just like the position and momentum operator. This just means that the operators correspond to something we can observe, like position and momentum. Now let's move on with the uncertainty principle by defining the variance of an observable A as sigma squared, which is written in terms of the operator A minus its expectation value or its mean value. Note that A is the ensemble of possible values of A. We can make things a bit neater by redefining all this in terms of f and write it in terms of bra f times ket f. Now this may look intriguing due to the notation, but it is just like the usual definition where the variance is equal to the value squared minus the mean value squared. Now we can do the same thing for a different observable B, where sigma squared B is equal to bra G times Kg, where G is defined in a similar way, where B is the observable minus its expectation value. So at the end of the day, we now have two equations for the variance of two different observables. If we now combine these two variances using multiplication and then use the Schwarz inequality, we can obtain that sigma squared of A times sigma squared of B, which is equal to the bracket of F times the bracket of G, which is less than the bra F Kg squared. But the last term can be treated just as a complex number and be rewritten so that we get that sigma squared A times sigma squared of B is less than 1 divided by 2i times bra F times Kg minus bra G times Kf and everything squared. And now recall that F and G are defined in terms of operators, thus they also follow the commutation relations as mentioned earlier. So we can rewrite the part in the parentheses in terms of the expectation value of our original operators A and B, such that bra F times Kg minus bra G times Kf, which is equal to the expectation value of the commutation relation between operator A and B. If you didn't quite get the last few steps, don't worry, the result is the most important. Finally, we can combine the equations from the last slide to obtain the general uncertainty principle, where the variance of observable A times the variance of the observable B is equal or greater than 1 over 2i times the expectation value of the commutation relationship between operator A and B and the right hand side squared. And this works for any two observables A and B. This equation can be used to obtain the uncertainty relationship between any two observables. Note that if the observables commute, then the uncertainty can be arbitrarily small. If we use our result from earlier with the position and momentum operator, we can obtain the most well-known uncertainty principle between the position and momentum, which is sigma x times sigma p is greater or equal to h bar divided by 2. And you can get a similar result by considering time and energy. This will be important in later videos. I want to make it clear that there are many observables in quantum mechanics, like angular momentum, spin, position, momentum, etc. Any combination of these observables which do not commute will have their own uncertainty principle. In this sense, there are many uncertainty principles depending on the operators you consider. A common factor is Planck's constant, and if we take the classical limit by setting h bar to 0, thus the limit which turns our quantum theory into a classical theory, then we see that the uncertainty principle becomes 0 and we get back our deterministic classical world without any built-in uncertainty. The uncertainty principle is however real, and if you ask any engineer who is working with microprocessors, then he will tell you about the problems they have because they are now making processors with transistors so small that the uncertainty principle is preventing them from having complete control of where their electrons are. This leads to the phenomena of quantum tunneling, which we will discuss in the next video. As always, I hope you liked this video. If you did, please comment, like and subscribe, and stay tuned for more videos.